whole schedule.
Well, it'll be messy. You can change it, but
You can change it.
yeah.
You're not going to get the teachers you want.
Yeah.
You're not going to get the classes you want. It's stupid.
Yeah, I think the administration needs to hear that from the students. We told them, but the faculty didn't like it. I mean, how many of us really know what? I mean, I had to pick my classes for spring 2024. Like, right? Like, I don't know. I guess there's pros and cons, right? But if you don't know what I'm talking about, normally you can register for like the next semester, right? That's it. Now you can actually register. They're going to open up registration. You can register for summer, fall, and spring of next year. You can do that a year ahead of time. So, yeah, if you don't know what you're taking, classes might fill up and then, you know. Okay. If you could get the quizzes together, why don't you all kind of get them grouped up and just have them all find their way to this center table right here. Or put them up here, whatever, either way. Yeah, here. Anyone else here? These. There we go. Those. Thank you. All right, thank you. All right, we're going to continue last class. Anybody want to recap like the main ideas of last class? Name? I don't see your name. Is your name on there? Okay. Do y'all remember what we were doing? What the main takeaway from last time was? What's that? Derivatives of exponential and log functions, right? So after last class, what we know now is how to take the derivative of exponential and logarithmic functions. The next thing we're going to do is we are going to talk about another category of functions that we need to be able to take the derivatives of, all right? And then we're going to move on to a new topic after that. So as it stands right now, there are 6 trig functions that we learn in pre-cal, right? There's sine x, cosine x, tangent x, cosecant x, secant x, and cotangent x. Right? Those are our 6 trig functions from pre-cal. And we in this class have already talked about what the derivatives of each of these are, right? We know that if we can take the derivative of sine and get cosine, we can take derivative of cosine and get negative sine. We can take the derivative of tangent and get secant squared. And then the next 3 I said you don't necessarily need to memorize, but the sooner you do, the easier Cal 2 will be for you. But we have formulas for these, right? They're on your formula sheets. So these derivatives, check, 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 right? All right, so what we're going to talk about now is that, again, in pre-cal, when you're learning these 6 trig functions, you're then taught that, you know what, there's these 6 trig functions, and each one of them has an inverse, right? There's sine, and then there's arc sine. There's cosine, and there's arc cosine. Or sometimes you say there's sine and there's inverse sine, right? Inverse sine and arc sine are the same functions. Do y'all remember hearing that in pre-cal? The inverses of all of these. Well, those are new functions, aren't they? The inverse trigs, the 6 inverse trig functions are written. Now the notation I'm going to use is this: sine with a little -1 of x. You could also have learned that in pre-cal this way, as arc sine x. Right? How many of y'all learned this notation? This one here? How about this one? So see, most learned it this way, but these mean exactly the same thing, all right? And there's 6 of these, right? There's inverse cosine, there's inverse tangent, there's inverse secant, there's inverse cosecant, in no particular order here, I'm just putting all 6 down, right? So you've got the 6 trig functions, and they each have derivatives. We have the 6 inverse trig functions, and guess what? They each have derivatives, right? So what we want to talk about are what are the derivatives of these, okay? What are the derivatives of these? So I don't want to get too deep into pre-cal here, but I just want to remind you of some things from pre-cal. So chapter 3, I'm going to erase everything I just put on the board. Chapter 3. Last class we covered 3.3. We are not doing 3.4. We're going to skip to 3.5, and then we are not going to do 3.6. You'll do that in Cal 2. All right? So 3.5, inverse trig functions. Let's do a quick recap of inverse trig functions from pre-cal, and then we're going to talk about their derivatives. So these are your, whoa, boy, I just got right to it. Oh, never mind. Guess we won't go through it. Here's what I'll say. Here's what I'll say. With the inverse trig functions, there are domain restrictions. Okay, because to have an inverse, your function has to pass the vertical line test and the horizontal line test. So there are some domain restrictions when you talk about inverse functions, inverse trig functions. But I don't want to get us bogged down on domains. What we want to talk about are just derivatives. Okay, so let's just do a first example. Find the derivative of the inverse sine function. Now, ultimately, this is going to be just a formula that you memorize or that you go and you look in your formula sheet. But I want to show you how we actually do it, all right? How we actually do this. All right, so here's what I'm going to do. I'm going to say, let's let y be equal to the inverse sine function, all right? And what I'd like to do is find the derivative of this. So I'm going to find here dy dx. Remember, this dy dx, all that means is the derivative, right? So I want to find the derivative of inverse sine. So I write down y equals inverse sine of x. And now I tell myself, OK, I'm going to go find its derivative. I don't know the derivative, right? So I'm going to use the only information I do know about inverse sine, and that's this. This is the critical step. What I know about inverse sine is that if I were to take this equation and take sine on the left side and take sine on the right side, what would happen on the right side? What happens when you put sine together with the inverse of sine? What happens when you put a function together with its inverse? They cancel each other out, right? And so all I get over here is what? X. So I get x over here. And over here I have sine of y. If y'all are coming in, I saw a few of you come in. I've already collected the quiz, so if you have it for me, please make sure. That makes sense, what I did there? I mean, it doesn't seem like this is going to get us anywhere right now, but do y'all follow the idea here? Yes? Okay. Now, at this point, is that both of you? Or? No. Okay, just yours. There we go. Thank you. So at this point, I actually do know what the derivative of sine is, don't I? Right? Sine, not inverse sine, but sine I do know the derivative. So I'm going to take that equation, and I'm going to take the derivative with respect to x on both sides. So what I'm doing here is implicit differentiation. Right, I'm going to take derivative on the left side with respect to x and the derivative on the right side with respect to x. Let's do the right side first. What's the derivative with respect to x of x? 1, right? This is 1. Now, on the right side, we have to use chain rule. So what's the derivative of sine of something? Cosine of it, cosine of y. Right? Am I done? No, what do I need next to this multiplied? Yeah, I have to take derivative of what was inside the sign, so I need to take derivative of y with respect to x, which would be dy dx. And isn't that what I'm trying to find? Right? I'm trying to find dy dx. So here's what dy dx is. dy dx times cosine y is equal to 1. So I'm going to divide both sides by cosine of y. One over cosine is what trig function? 1 over cosine is secant. Secant, right? So you've got dy dx equals secant y. We have an answer, don't we? It's kind of weird, isn't it, the way I did that? Right? I wanted to figure out what the derivative of inverse sine was. I don't know what it is, so I took sine on both sides, right? Took that new equation, differentiated it implicitly with respect to x, and then when I do that, I'm able to solve for dy dx, so I have an answer, right? But there's a problem with the answer. The problem with the answer is that our original trig function had what variable in it? X, right? And our derivative has what variable in it? Y. So what I want to do is I want to see if I can get this answer back to something that has x's instead of y's. Understand? Just so that it kind of makes sense. It's like when I say what's the derivative of x squared, you say 2x, right? You don't start talking about y's, do you? So our answer has y's. Let's get it to x's. So how do I get back to x? How do I get back to x? This right here is a big step, especially like almost all of you need Cal 2, right? At least half of you need Cal 2. Okay, the next thing I'm going to do right now is used in Cal 2 a lot, and it's called creating a reference triangle. And so pay attention, all right, to this next step. What I want to do, again, is try and get this answer to have x's and not y's. So I go back to this stage right here, that equation right there, and what I'm going to do is from that statement right there, I'm going to draw a triangle. Let me draw it first, then you'll hopefully understand what I'm doing. I'm going to draw a right triangle. This is called a reference triangle. So what I'm going to do is I'm going to use what this says here to create the triangle. So this says sine of y. Whatever's inside of a trig function is the angle, right? Normally in pre-cal this is like sine theta, isn't it? But here the statement is sine y. So my angle is y. The angle is y. I'm going to put that right here. That angle is y. Now, sine, by definition, is which side of the triangle divided by which? SOHCAHTOA. Opposite over hypotenuse, right? So look at the other side here. X, I want you to look at that as a fraction. X over 1, right? That's the way you could rewrite x over 1. And if you do it that way, you can look at the x as being the opposite, and then you can look at 1 as being the hypotenuse, right? So I'm going to label my triangle like this. Now, if that's a little fuzzy in your mind, like what I'm doing here, let me ask you to think of it a different way. If I gave you this triangle right now and asked you what's sine of y, what would you tell me? X over 1, or x, right? So sine of y would be x, right? And that's what that's what that says, right? Sine of y is x. Do y'all see how I'm using the equation to create the triangle instead of the triangle to create the equation? Going backwards. Now, any questions? Why did I do that? Well, I did that because I want to know what secant of y is, right? Secant is the reciprocal of cosine. Cosine, SOHCAHTOA. Cosine is what? Adjacent over hypotenuse. Secant's the reciprocal. So it should be hypotenuse over adjacent, right? So this right here is the hypotenuse over the adjacent. Let me mute my phone. My daughter's Well, my wife's at an awards ceremony for my daughter, and she must be sending pictures. Okay. All right, so hypotenuse over adjacent, right, is what I need off that triangle. So I need hypotenuse, I've got it. Do I have the adjacent? No, but I have 2 of 3 sides on a right triangle, don't I? So if I have 2 or 3 sides, I need to know what this side is. Let me call it A, right? I need to know what A is. If I can figure out what A is, then I'll be in business. But we have Pythagorean, don't we? We have that this squared plus this squared is this squared. So I'm going to write that down up here. So I know that A squared plus x squared must equal 1 squared. That means that A squared equals 1 minus x squared. So all I did there was just squared the 1 and then brought the x squared to the other side, right? Just subtracted x squared on both sides. And then finally, I'll take the square root on both sides. And now I have what A is, right, in terms of x. So this A is square root of 1 minus x squared. I'm ready to rewrite this answer now, right? Secant of y is equal to the hypotenuse of that reference triangle over the adjacent side. The hypotenuse we said was 1, and then the adjacent side is the square root of 1 minus x squared. And that's my answer. You see our derivative has x in it, which is what I was hoping to get, right? It's weird. You don't have to be able to go through this. In your homework problems, there is, I believe, one problem where it asks you to verify, like show what the derivative of cosine inverse is, and then you would do the same sort of thing. I'm not going to put this on a test, all right? I just want you to see where it comes from, because it's kind of weird. To me, it's kind of weird. When you take the derivative of sine, you get cosine. Derivative of cosine, you get negative sine. So with the regular 6 trig functions, when you take their derivatives, you get trig functions. But when you take the derivative of an inverse trig function, you're not getting a trig function, are you? You're getting some other weird root function in here. So it just doesn't seem like it seems like it should be a trig function or something, right? It's not. Okay. So I could do this same setup for all 6. I'll do one more. How about I do one more? Because enough of you need Cal 2. The reference triangle is worth seeing more than once. Let me do one more of these. Let's find the derivative of the inverse tangent function. And I'm going to put here on the side what we just figured out. We just figured out that the derivative of sine inverse of x is 1 over the square root of 1 minus x squared, right? That is on your formula sheets. All right, it's there. I'll show that to you in a minute if we need to look at it. Okay, following the same procedure that I just did, what would I do first? Set that equal to y, right? Put y equals this. Right? First we set it equal to y. We do that so we can do the next step, which would be what? I don't know anything about the inverse tangent function, right? What do I do know about? Tangent, right? So how am I going to do what? Take tangent on both sides, okay? Take tangent on the left. Take tangent on the right. On the left, nothing changes, tangent y. On the right, tangent of tangent inverse, they kill each other off, and you just get the x. I've collected the quiz if you have the quiz. You can just put it right there on the corner. Make sure your name's on it, though. That all okay? That's the same procedure, right? What did I do? What did I do next? Do what? What did I do at this step? I took the derivative, right? Implicit differentiation, both sides, with respect to x. So let's take derivative with respect to x on the left. And then let's take the derivative with respect to x on the right. What's the right side? The right side, the easier side. 1, right? And the left side, careful there. What's the derivative of tangent of something? Secant squared. So secant squared y. I'm not done. Times what? You got to take derivative of what was in there, right? Derivative of y with respect to x is dy dx, which is what I'm trying to solve for, right? Trying to find dy dx. So there it goes, appearing again. Okay, get dy dx by itself on one side. So divide both sides by secant squared. One over secant squared secant squared y. I almost put x. Look at our answer. It has y in it again, doesn't it? Okay, it has y. I want it to have x. So, the squared is a little bit of an issue. A little bit of an issue. But let me see if you believe this. Do you agree that this is the same as 1 over secant y squared? Because that's what that means, right? This means this. And then this step is a little bit strange, but just look, isn't this the same as this? Right? If I take this fraction and I square it, you square the top and the bottom. What happens if I square 1? I get 1, so that's that. And if I square this, I get that, right? So this is the same expression, right? But what is 1 over secant? What's the reciprocal? What's 1 over secant? Cosine. Cosine, right? So this is just cosine y, right, squared. All right, that's what that is. Y'all with me? Any questions? We're not done, right? Yes?
Is it always going to cancel out?
Yes.
The tangent and tangent?
Yes.
Like for every problem?
Exactly. So if this was cosine inverse, right, I would get to this step, I would do cosine on both sides, and the right side would cancel out, you just get x. All 6 inverse trig functions would work the same way, all right? So my answer, the derivative of inverse tangent of x, the derivative of inverse tangent of x is cosine of y squared. See, our answer has y. I don't like that. I want it to have x. So I need now a reference triangle. Okay, I need a reference triangle. My reference triangle is going to come off. The hard part is figuring out where does your reference triangle come from. It comes from as soon as you do this step, the step after it right here. That's where it comes from. Tangent of an angle, tangent SOHCAHTOA. Does everyone know what I'm saying, SOHCAHTOA? You sure? Yes? Anyone not? It's okay if you don't. No? Anyone? No? I actually used SOHCAHTOA yesterday. Well, I didn't use SOHCAHTOA. My dad did. He was doing something, trying to find. It was actually this problem. I'm building a mirror. It's 9 foot tall, and it needs to be 1 foot off the wall. So it's 9 feet this way. No, yeah, about 1 foot off the wall. So it's going to lean. It's got to be 1 foot, and we were trying to figure out what that angle is. So that's theta, right? Cosine of theta is 1 over 9. So if I want to know theta, I take cosine inverse on both sides. So you just get on the calculator and do cosine inverse of 1/9, and you get your angle, right? But my dad was trying to do it before I was out there helping him, and he remembered SOHCAHTOA. I was pretty proud of him. He's an old man. Okay, so there's my triangle. I mean, there's where my triangle is going to come from, right? I'm going to draw my triangle. What's the angle? What do I call that angle? Y. Okay. And tangent is, SOHCAHTOA is which side? So I'm going to create the fraction again. I can always do that, right? This over 1. So that means the opposite side is what? X, and the adjacent side is 1. So you can't use the same triangle we did in the previous problem, right? It's a different setup. And what am I interested in? cosine of that angle, right? Cosine of that angle. Well, for cosine, I need adjacent over hypotenuse. I don't have the hypotenuse, do I? But I can go get it. So I can call this h, and then I know that 1 squared plus x squared equals h squared. If you square the 1, you get 1. If you square the x squared, it's just x squared. And then you take the square root on both sides, right? And you get square root of 1 plus x squared. That goes here. Questions? So this becomes, up here, cosine of y, which is 1 over adjacent over hypotenuse, which was square root of 1 plus x squared. And now I square the top and the bottom. And actually, this is really nice. If I square the top, I get 1. If I square the bottom, I get 1 plus x squared. And that is your derivative. Right? You square the square root on the bottom, it goes away. We've done 2 of the 6, right? I could keep doing this. I'm not going to do 4 more of these. I think you get the idea, right? Yes? The only way you'd see a problem like this on a test is as a bonus. That's the only way I'd ever give a problem like that. Not that I think it's hard or anything like that. It's just that what we're more interested in is we know what the derivatives are. Now can we use those derivatives along with chain rule, product rule, quotient rule, all the rules that we've learned, you know, up to this point. So let's summarize these six inverse trig functions and their derivatives. On your, like I said, on your formula sheets, these are there, right? These are there. Again, Cal 2 students, the ones that you're probably going to find you're going to find yourself using, and at some point you'll probably memorize. Let me make this a little bigger. That first one, for sure, okay? We just proved this one. That one we use a lot in Cal 2, okay? This one shows up every once in a while. Notice the difference. Look at these two. There's only one difference between these two derivatives, right? That one's positive, this one's negative. That's it. That's the only difference between the derivative of inverse sine, inverse cosine. Inverse tangent, I just proved this to you, didn't I? We just proved this. This is the derivative. And then you get other derivatives. Now the next 3 you don't use very often, okay? These do not come up in Cal 2 very often. But again, we could have done the same procedure and proved that these formulas. Okay? So just know that they exist. That's the big thing. Know that they exist. Any questions? No? Okay, let's do yes.
I just wanted to clarify. So the process we did as far as we took the left and the right.
Mm-hmm.
Let's say we had a bonus question. That's the same for all of the
That all the inverses would go the same way. Mm-hmm. The procedure is the same. Y equals the inverse trig function, right? And then you take whatever trig function on both sides to make it cancel. Then you differentiate, right? Then you solve for dy dx, and then you create a reference triangle, and then you get your answer. All right, so now let's see if you can now blend those new formulas with some old stuff and some newer stuff. So how about this? If y is equal to x squared inverse sine x, find y prime. Find y prime. So take the derivative of that. So what do you see here? Product. Everyone see that multiplication? It's x squared times inverse sine x, right? So in order to take that derivative, we have to do the product rule. So the derivative of this would be, well, here's my product, right? It's the derivative of the first one, which is 2x, times sine inverse, right, with no derivative, right? No derivative on that one. Plus, now the derivative of sine inverse x, which is that right there, right? 1 over the square root of 1 minus x squared, right? Am I done? Times x squared. That's it, right? And then the most you could really do here is just take that x squared and put it up in the numerator here. That's about all you could do to clean it up. I mean, you could try and get common denominator, but really, put the x squared up there, you're done. Okay? Questions? Do another one. What if y is equal to sine inverse of x squared plus x? That's different. Same instructions, find the derivative. What do you all see here? Chain rule. This is composition, right? This is not a product. What's happening here is you're doing sine inverse of x squared plus x, right? The x squared plus x is the argument of this trig function, this inverse function. It's the thing being plugged in. So you have the chain rule. So what's the outer function here? The inverse sine, right? That's the outer function. So you have to start with the derivative of that, which is this, right? But chain rule, you have to be real careful with this. So the derivative of this would be, and this is where we can go back and use that thing that I did before when we were learning chain rule, right? It's like, what's the derivative of sine inverse of these markers? According to that, it's what? 1 over the square root of 1 minus, now is it x squared? What is it? My markers squared, right? It's my markers squared. It's the same chain rule we've been doing, right? So under here, don't put x squared. You put x squared plus x, what? Squared. Everyone see that? The derivative of arc sine or inverse sine in my hand is 1 over the square root of 1 minus my hand squared, right? Derivative of inverse sine of x is 1 over the square root of 1 minus whatever that x is, whatever it was, right? Whatever that argument is, squared. Am I done, though? No. What do I need to do now? Multiply, right? Chain rule. So multiply by the derivative of what was in here, which is 2x plus 1. Do I need that in parentheses? Yes. Because it's two terms, right? So this must be in parentheses. And then let me go one more step. I'm going to take that and slide it and push it up to the top, 2x plus 1 over square root of 1 minus, and then the bottom x squared plus x squared. I'm not going to actually square this out or FOIL it out. I'm just going to leave it just like this. That's my derivative. Y'all see how this works? Y'all see why chain rule is so important? Like it